Hi folks, this is your talking head again. We're going to be talking about light as a wave and its usefulness in telescopes. So the first set of charts here is going to be concentrating on electromagnetism and light. So to remind you, there are four forces in nature, and we've gotten done speaking about gravity, and now we're going to be talking about electromagnetism. The strong and the weak forces are those forces that hold nuclei together and cause radioactivity. All right, so let's get to the next chart. It's just a pretty chart. What is the point of all this? Well, in conjunction with next week, we're going to be talking about light. Light is through which we observe the world. It is the way that we touch. There are few forces that are as natural as light, although we don't really recognize it as such. We recognize gravity as being the natural force in our lives. But look around us, the technology involved around us is almost entirely electromagnetic in nature. All right, so what are the things that we want to do? Well, as you can read the chart, there is quite a lot of things that we want to do. We want to be able to characterize light and matter. What is a wave? What is a particle? How do these things interact with each other? Excuse me. What is the connection between temperature and light? And then there are two laws that have simple phrases associated with them. And they describe how light behaves very accurately. The first one, Wien's law, is basically goes as the hotter something gets, the bluer it is. And then the Stefan Boltzmann law is basically the hotter something gets, the brighter it is. So those are two simple phrases that describe a lot of physics about what is going on with light and how we can read, if you will, the stars in the night sky. To start off with, this is probably something you know, but the world around us is made up of electricity. When you shuffle across the floor, you can pick up static electricity. Lightning is the natural byproduct of static electricity, and we have these things called charges. In atoms, charges are made up of negatively charged electrons and positively charged protons. The charges feel force that is very reminiscent of the gravitational force that we saw last week. Force there is equal to a minus sign because it can be attractive. It is attractive in one case, but it's also the electrical forces can oppose each other. You probably heard, likes attract. Likes repel and dislike and unlike things attract. And that's partially due to the fact that we do have these two charges, and they can have positive or negative values. And this constant here is something that we recognize as, if we, it allows us to convert chargeness and distance into a measurement of how much pushing or pulling we've got. That's what we saw with gravity before. But the force is proportional to the charge of one guy, the charge of the other guy, and the distance between them. It has the same form as what we saw with gravity. The difference being is that the charge for gravity and its force is so much less than what we see with electromagnetism. 20 orders of magnitude difference. It's hard to recognize how significant that is. Now, just like the solar system, we can create, if you will, an atom where electrons go around, the big point mass in the center called the sun. And we basically, this manifestation here is the hydrogen atom. And we basically have in the old model, it's called a Bohr model, describes it as a point charge, a point electronic charge, an electron, and it goes around and around and around the proton, which is in the center. Now, notice here, well, it doesn't really show up in this picture very well, but most of the atom is just space. There's nothing in it. This proton is a point charge, and it is 1,000 times smaller than the size of the atom. The size of the atom is basically a representation of where the electron is at a given point in time. Not really a point in time, because when you get so small, you can't really precisely define a point in time. If you add another electron and proton, then you get helium, and we also add a couple more of these green guys here. Those are neutrons. And when I was younger, basically really young, I'm talking about in third grade summer school, I had a teacher who provided us a study in the periodic table, and what I found out was that basically you could add protons and neutrons together, and when you did that, then you could create the whole periodic table. So here is lithium. We just add another proton and another neutron. And to remind you, neutrons are there. They provide the glue for keeping the nucleus together, because after all, look at, we have a bunch of positive charges here, and aren't they supposed to repel each other? Well, yes, they do, but the nuclear force with the neutrons in there causes them to stick together into the center there. Okay, so here we have the periodic table, and what we see with it is it's very important. This is one of the key things associated with history, and we start off here with hydrogen, and as we go in one particular column, we get to heavier and heavier materials, and then as we go across, we get heavier and heavier as well. The point here is that we're going to be adding protons and neutrons as we go across, and we have found that those items in the same column behave chemically the same way. And so hydrogen, lithium, sodium, potassium, and then beryllium, magnesium, calcium, and then all these guys are very similar. And then when we move over here, we have a lot of activity going on: boron, aluminum, gallium, carbon, silicon, and germanium. These two we use for semiconductors, and people are now learning how to use carbon as a semiconductor. But you probably have seen various science fiction stories where we have silicon-based life. The Hortas of Star Trek are a case in point. And then over here we finally end up with the noble gases. Basically, these gases don't interact well with others. They, in the sense that they do not chemically form any compounds. Everything over here on the other side of those guys do form chemical compounds. Let's see if I can show you this again. Fluorine, it behaves like chlorine. It's very reactive to these guys over here. They want to share electrons in a particular way, and it's called a polar molecule. Carbon, on the other hand, when you create methane, this is a covalent bond, and covalent bonds are actually more like sharing more like sharing the electron rather than basically absconding with it, which is sort of what happens with a polar molecule. Okay, basically what we want to pause here Okay, here we're starting up again, and this is sort of the way that we visualize light traveling as a wave. And waves we're very used to. Basically, electromagnetic radiation is what we term as light. So if we continue on, light is a wave, very similar to what you see here. And these sets of waves are very characteristic of electromagnetic light or waves as well. We have a distance between the high points in the wave, which we call crests, and we have that same distance is between the troughs, the low points in the waves, and that distance is the same. This is called a wavelength. And you can see on here on the surface waves on the water, they're very, very regular. And that's what we have with light as well. It's called a wavelength. I mean, we physicists are very, very clever in that respect. And it's basically, we use the Greek letter lambda to describe it. Now, the wavelength is the distance that, the physical distance from one portion of the wave to the other. Now, you got to be careful. I mean, it's pretty obvious for the high points and for the low points, but when it crosses the midpoint, you do have to be careful. You have to be going in the same direction. The wave has to be either going down or going up. Okay, so if I'm taking the going down method, then the wavelength goes from here to the next point that the wave is going down. And the similar situation applies when the wave is going up. So if I start here, then I have to wait all the way around until it comes back up again. Okay, so that's how we define wavelength. Now, the other thing that we can define is how long it takes to go from one crest to another or one trough to another. And how I describe it is, imagine you're over here on this little island, and I can ask the question, when will I get wet again? Namely, when will the crest come over and get me wet or the wave break? Well, that is a period of time. All right, so, and it takes a certain amount of time to do that. One period is the time it takes for one crest to pass a point and then for the next one to arrive. Now, the other thing I can ask is how many times do I get wet per second? And so that's a measure of the cycling frequency of the wave. Okay, so here we have a picture sort of indicating how frequency and period work together. So a short period means a high frequency. Low frequency means a long period, so a high number. Okay, so basically you can gather from that, and you would be right, that frequency is the inverse of the period of a wave. Electromagnetic waves don't require a medium to travel in. And what I mean by that is light travels through the vacuum of space, simply put, and it always travels at a particular rate in the vacuum of space. You probably heard that the ultimate speed limit is the speed of light, and that's its value, 3 times 10 to the 8th meters per second. Remind you, a meter is approximately 1 yard in distance. Now light also travels, that is equivalent to having a light wave go from one hand to another hand, going about a foot in a nanosecond. Now, one of the tests I like to show my students in class is to show an example of various waves, but I can't do that for you, maybe in another episode. Okay, well, one of the characteristics of wavelength is, for us, we visualize it in terms of color. So here, what I've got is a picture showing, the frequencies of light that we can see, and I will alternately just use frequency or wavelength because they are connected to each other. The speed of light is equal to the multiplication of wavelength and frequency. So you speak of one, then you speak of the other. So the wavelengths that we nominally see are from 450, which is violet in color, over to about 750, which is red in color. On the other side of 750, we have the infrared radiation, or heat, if you will. And then over here on the, as we get more violet than violet, that's the ultraviolet set of frequencies. The wavelengths of light, visible light, are very small in comparison to the other wavelengths we have. And going from high energy, which is very small wavelength or high frequency, we have gamma rays, and then we have X-rays. Then we go to ultraviolet waves, which we just spoke about, and then visible light and infrared, which is synonymous with heat radiation. Radar is part of the radio waves, which includes all these guys. So FM, TV, shortwave, and shortwave and AM radio. Okay, to give you an idea of what these things are, gamma rays, the shortest wavelengths, basically produced in such dangerous things here. They are dangerous, and most of these things are absorbed in the atmosphere, thank God. X-rays are also very dangerous in the sense that they can alter your chemistry, and they basically break apart the nuclei in the atoms in your body. So that's why when we go to the dentist or the doctor for various X-rays, they only use a specific short amount, as small as they can get, and then they cover the rest of your body with lead aprons. Good thing. You probably, well, I don't know, this is maybe more of my time as a youth, but we had these black light posters, and the black light would produce ultraviolet radiation, which would hit specific paint, and that paint would glow. And so you would have this light in a room that was dark, and then you would have these posters that would glow in the dark. Ultraviolet is not something that we can see, but we can get skin cancer from it, obviously. So it is mostly absorbed by the atmosphere as well, but not all of it. Visible light comes in the in a variety of flavors. You can remember with the mnemonic Roy G. Biv, so red, orange, yellow, green, blue, indigo, and violet. We don't really do indigo anymore. When you add all the colors together, you do get white light. Infrared radiation is that which you feel. So feel it on your lips, on your skin, things like that. When you are far away from a campfire, you can feel the heat from the campfire. Radio waves, well, we're used to that. Cell phones, example of that. Internet, Ethernet, all those things, that's radio waves. And the wavelengths there are quite large. And people use all sorts of frequencies, and it has to be correlated. So you don't transmit over the same frequency. So that's why we have different radio stations, as an example. All right, let's see. We'll stop here for the moment. And, well, let's see if we can get these songs to play. It's a very, I guess we can't do that. We'll try again. Okay, we'll pause here for a moment.